Hello and welcome to this FMSP online revision recording for the OCR specification Module M2 Mechanics, and the topic is Equilibrium of a Rigid Body. Under that heading in the specification there are three sections. The first one says that we should be able to calculate the moment of a force about a point, and then the second section reminds us that for a rigid body to be in equilibrium, two things must apply, and the two conditions are that the vector sum of the forces must be zero, so there's no overall resultant force, and secondly, the sum of the moments of the forces about any point must also be zero. In short then, for every equilibrium question we have two tools in our kit bag to use: resolving forces and taking moments. We want to be sure that the resultant force in any direction is zero, and that tells us that the rigid body is not moving or accelerating in any direction. And then secondly, that the sum of the moments about any suitable point is zero, and that tells us that the rigid body is not rotating. Well, we're going to use these conditions to solve problems involving equilibrium, including those that involve toppling or sliding, and I've chosen an example of that as one of my two exam questions. So here's some key points. First of all, for equilibrium of a rigid body, here are the two things we do: resolve forces and take moments. So the resultant force in any direction that suits us must be equal to zero, and the total moment about any point must also be zero, or perhaps we will use the fact that clockwise moments will equal the anti-clockwise moments. Now, when a rigid body is on the point of sliding, when it's about to slide, it must be in limiting equilibrium. In other words, the friction is maximal and only just enough to hold it in place as it stands. Change the forces a bit and it will slide. Then, when a rigid body is on the point of toppling, the weight will act at an extreme point of the base. If, for example, it's a crate at rest on an inclined plane, then the weight force will be acting through the lowest point of the base when it's on the point of toppling. And for toppling to take place, the line of action of the weight must be outside the range of points where the rigid body is in contact with the surface in question. So let's look at a couple of questions together, and here's the first one. A non-uniform beam AB of length 4 meters and mass 5 kilograms has its center of mass at the point shown. Well, we can see that's off center because it's a non-uniform beam. The beam is freely suspended from a hinge here at A. Not really sure about the forces acting through there, but they're holding it at one end, and then there's a wire at the other end, so there's a tension force in this wire, and that's keeping the beam horizontal. It's holding the end B up. Well, we've got two things to do. First thing is calculate the value of that tension, and then secondly calculate the magnitude and the direction of the force acting on the beam at A. That's over here, so I will need to find that force. Okay then, remember we've got two things to do: resolve and take moments. I'm going to start with a new version of the diagram, and remember my two key tools: resolving forces and taking moments. Well, I want to put on here that weight force. We're told the weight of the beam is 5 kilograms, so that weight force is 5g newtons. Then there's the reaction force here I'm not so sure about. When I'm not sure about a reaction force, I usually put in a horizontal component and call it x, and a vertical component and call it y. And if I was resolving components, I'd need both of those, which makes me think that probably to find the tension I'm going to, instead of resolving forces, I'm going to take moments. And if I take moments about the point A, I can ignore the forces acting through A. But I will need to think about this tension force at the end then. So this force is acting at an angle, and so I'm going to split it into two components, a vertical component and another component here, horizontal. The vertical component is next to the angle, so its magnitude is t cos 20 degrees. And this horizontal component up here is t sine 20 degrees. But although, for convenience of drawing the diagram, I've drawn the force at the top there, in reality it acts also at the point B at the bottom here. So the line of action of this t sine 20 force is through the point A, which means I can ignore that when I'm taking moments. So let's take moments then, and I have a force of t cos 20, that's the component that's perpendicular to the beam, acting at a distance 2.5 plus 1.5, that's 4 meters away. And that's equal to the turning effect of the 5g newtons force. This has a clockwise turning effect, whereas the tension has an anti-clockwise turning effect. So the magnitude is 5g, and its distance from A is 2.5. Well, that's done that. So the tension is 5g times 2.5 divided by cos 20 degrees times 4. And calculating that gives me a value for T, which is 32.6 newtons. Now, throughout this question, there are various values which we continually keep reusing. And for example, this tension is really 32.5904, etc. I shan't write it down, but I've stored the fully exact value as given to me by the calculator for use in later steps, so that I don't lose accuracy later on. Well, that's the tension rounded to 3 significant figures, and that's the first part of the question done. There are 3 marks for this part. The first is a method mark for correctly taking moments about the point A, and then there's a second method mark for getting the correct statement having taken moments, and then of course there's a mark for the answer. Well, we found the value of T, and now we have got to find the magnitude and the direction of the force acting on the beam at A. So once again, let's draw in. I don't really know what the force is like, but I'll consider components in sort of normal x and y directions and see what I make of those. And pretty clearly, having last time taken moments, on this occasion I'm going to have to resolve forces. So I'll need to consider what's happening horizontally and what's happening vertically. I'll start with what's happening horizontally, and once again I'm going to pop back in the components of this tension force over here. So we had t sine 20, it's sine when it's opposite the angle, and t cos 20, it's cosine when it's next to the angle, and of course the weight force of 5g newtons. So, horizontally, forces to the right equal forces to the left. So the forces to the right are x and t sine 20. Well, wait a minute. Both of those are to the right, and there's nothing to the left. Well, I'm not worried about that. It just means that, in fact, my value for x, I should find x pointing the other way. The way I've drawn x, I'm going to end up with minus t sine 20. And I know t from the previous calculation is 32.6, and multiplying that by sine 20 gives me minus 11.1 newtons to 3 significant figures. So the minus sign is just correcting the direction for me. Well, now let's resolve vertically. And upwards, clearly we've got y plus t cos 20 upwards, and that's equal to the only force downwards, which is the 5g newtons force. Well, once again I can move everything over to the right and say that y equals 5g, 5 times 9.8, minus t, which you remember was 32.6, times cosine of 20 degrees. So I have all the information I need to work that out, and that gave me a value for y which actually came out exactly to be 18.375. However, I'll round it to 3 significant figures because I feel I ought to, but I will be using the exact value in subsequent calculations. So what does that tell me then? Well, if I imagine my point A over here for a moment, that tells me that I've got a component acting to the left of magnitude 11.1 newtons and a component working upwards of 18.4 newtons. So if I want to know the magnitude and direction of that force, I'll find the magnitude of this reaction force at the hinge by Pythagoras, because it's a right-angled triangle, and I think I'll find this angle down here, the angle from the horizontal. So, from that I've got that r is the square root of 11.1 squared plus 18.4 squared. And calculating that gave me a value for the reaction force at the hinge of 21.5 newtons, to 3 significant figures. And then to find theta, while looking at my diagram, I have tan of theta. Tan of theta equals opposite over adjacent, 18.4 over 11.1. And therefore theta is inverse tan to the minus 1 of 18.4 over 11.1. And that gave me a value for theta, which I calculated to be 58.8 degrees to 1 decimal place. And given my diagram, that looks like about the right sort of angle that I'd be expecting. And I also made a little note under that to say that this was the angle above the horizontal, although I think my diagram does make clear which angle I mean. Well, there's 7 marks for this part of the question, and they're allocated as follows. There's 1 mark for correctly resolving forces horizontally, and then a mark for getting the right value here for x. There's a 2nd mark for resolving vertically, and a mark for getting 18.4 as the value for y. That's 4 marks so far, 1 for using Pythagoras and 1 for the answer for the magnitude of the force. There isn't a separate mark for using inverse tan, but the 7th mark is for finding the angle theta. And just to say that this isn't the only possible method to use to find the magnitude and direction of the reaction at the hinge. So if you used a different one, just check with the published mark scheme to see if yours would score full marks. Well, let's move on to another question then. And this one involves sliding and toppling. And what we have in front of us in the diagram is a cross-section through a cone lying on a flat surface. So of course the curved cone is only in contact with the surface along the sort of line that we see in the diagram here. And we have a point V, and take your time to read the question, pause the recording if you wish to, but we're told that as this force acts, the cone is going to topple about the point V. So what else do we know about it? Well, it's got a weight of 550 newtons, and that must be acting through the centre of mass. Well, the centre of mass must lie on the line of symmetry, the axis of symmetry, and I'll fill in some details about that on the next page. We're asked to find the least possible value of the force F so that the cone is going to topple. So what we're going to do is find that limiting case. So here's the diagram again, and let's label onto it what we need. First of all, I want to make a note about the weight. The weight is 550 newtons, and it acts at the centre of mass, which I'm going to call C. Now I've removed the 0.8, which was written to the right of that line. I'm just going to write it again here on the left. V to this point here, which for reference I'm going to call M, is 0.8, and the centre of mass is somewhere along that line. In fact, it's not too difficult to find. You just look it up in the formula book, which tells you that for a solid cone, the centre of mass is 1/4 h above the base. Well, here, the base is the line QP because it's been tipped over onto a curved surface, and MV is the height. It's of length 0.6, so MC is 0.2. And that means that this weight force here is acting at a distance 0.6 from V, where it's going to topple about. And I'm just going to note that way the examiner can clearly see it, rather than just leave it scribbled on the diagram. 0.6 meters from V. Well then, as it's going to rotate, this is a question for taking moments. And we'll take moments about V, and when it's on the point of toppling, those moments will be equal. Right, so the first thing is, if I'm taking moments about V, I need to consider the moments of this force F. Well, the line of action of F passes through M, and the line VM is perpendicular to that. So the perpendicular distance from V to the line of action of the force is 0.8 meters. So I've got F times 0.8 for the moment of that force, and that is an anti-clockwise moment about V. The weight force will give us a clockwise moment, so those two are going to be equal. And in the little triangle V to C and following the line of the weight force, that angle is also 60 degrees because of the symmetry of the cone, which makes the little distance from V to the line of action of the weight force easy to work out by cosine. So I have 550 newtons for the weight force. I need to multiply that by the distance from V to the line of action, which is, from that triangle, 0.6 cos 60, because it's next to the angle. Well, there we go. So F is equal to 550 times 0.6 cos 60. Now, wait a minute, cos 60 is a half, so 0.6 times a half is 0.3, and I've just divided both sides by 0.8 in order to work out the value for F. Well, this particular value is 206.25 newtons. So I'm just a little bit loath to write it to three significant figures, because if I write F to be 206 newtons to three significant figures, let's just see how that fits with the wording of the question. Now the question says, calculate the least possible value of F. So I think that in order to topple, I would want to write that F has got to be greater than a least value of 206.25 newtons. I don't really want to write F has to be greater than 206, because that's already rounded down from the critical value. Well, that part of the question is worth 4 marks, and they're allocated as follows. Correctly choosing to take moments about V is worth a method mark, and then getting the left-hand side is worth 1 mark and the right-hand side is worth another mark. That's 3 of the 4 marks. Rearranging to get the final value for V is worth the 4th mark, and 206 newtons to 3 significant figures is acceptable according to the mark scheme. Well, now then, the situation's going to change. Now we're told that if the force at Q acts at right angles to the base of the cone and increases to a point where something's going to give, we're told that the cone is going to slide before it topples. Now obviously if you're lifting the point Q up, if it's going to topple about P. so I'm going to need to take moments about P to find out something about the tension force. But if it's going to slide first, then I need to find out something about mu. Now I'm not given mu, but I'm going to work out the value of mu, and obviously if mu is very small it'll slide straight away. And the question is, what's the greatest possible value of mu so that it will still slide before it topples? Okay, holding all that in mind, let's draw what we need to on the diagram. And there's quite a bit of information that I need to add to the diagram in order to answer this. So be patient with me as I add in some lengths that are needed. First of all, I realise I'm going to have to take moments about P, so when I do, I'm going to need to know the distance PQ, because that's the distance to this force T. Okay, so what's PQ? Well, I can work it out because I know I've deleted it here from the diagram, but the distance VM is 0.8, and given I know the angle 60, that means that MQ is 0.8 tan 60. So the total distance PQ is two of those. Two lots of 0.8 tan 60 degrees. And I'm going to use an exact version of that because 2 times 0.8 is 1.6 and tan 60 is exactly root 3. So there we go, without any loss of accuracy, that's the length PQ in meters. I'm also going to need to know the length VP. So from V to P, well, what do I know in here? Well, once again, I know the 0.8 and I know this angle is also 60 degrees. And if I want to know VP, well, if that was the hypotenuse, I would be able to say, if this angle is 60, that VP cos 60 is 0.8. Sorry, VP sine 60. VP, yes, pardon me confusing myself. VP cos 60 is 0.8. Okay, that means that VP must be 0.8 divided by cos of 60. Well, cos of 60 is a half, so the top is 0.8 and the bottom is 0.5, which means that VP must be exactly 1.6 meters. Again, useful little fact to know. And of course I still have, at the point C up here, the weight force acting, and that's my 550 newtons. Well, there's other forces acting. There's a frictional force, which, as the last point to be in contact, if I pull up Q, is going to be P. I'm going to mark the friction acting down here. So a horizontal force of the friction there, given a value of mu that I need to find in a minute. Again, if you lift Q, the last point in contact with the surface will be P, so I'm going to mark the reaction force as being over here, but I do have a reaction force upwards whilst the rigid body is in contact with the plane. And still a little bit more to go on. I'm going to drop a vertical line through the point Q because I want to convince you that this angle in here is 30 degrees. And we can see that with 60 and 60, that angle is 60 degrees. Clearly that's 90 degrees, which makes the angle in here 30. Then if you take the triangle VMQ, there's 60 and 90, so that angle is 30. And because we have a right angle between PQ and the angle and the force T, that only leaves 30 degrees, so there's 30 in there. Now I'm doing that because I want to find components of this tension force. The one up here will be T is next to the angle, so it's cos 30. T cos 30, and the component there, T sine 30 degrees. I think finally I've written everything on the diagram that I'm going to need to complete the question. So we're now doing part 2, and we're going to consider what the tension's going to be when it's on the point of toppling about P. In other words, the moments are going to be equal about P. Here we go then. Moments about P. So taking moments about P, what have we got? Well, first of all, there's this tension force, and the line PQ is the perpendicular distance to the line of action of that force T. So it's T times the length PQ, which we've already established is 1.6 root 3. Well, that's got to be equal to the turning effect of the weight force, which is the only other force outside the point P. So the weight force is acting downwards, its magnitude's 550, but what's the distance from P to its line of action? Well, I want the distance from P across here. Well, the distance all the way from P to V is 1.6, but of course that's too much. I'm going to need to subtract from that the little part here, which, seeing as this is 0.6 for the distance VC, that little length is 0.6 cos 60. Well, since cos 60 is a half, this bit over here is in fact 550 times 1.6, take away half of 0.6, 0.3. So if I divide through, T is all of that divided by 1.6 root 3. And if I carry out that calculation, I'm going to get 258 newtons. So there's the critical value for the tension, and at that value the rigid body won't topple, it's just on the point of toppling. That of course is 3 significant figures, but I didn't feel too bad about rounding that one because the calculated value is 258.003. Okay, I'm just going to remove this shape, there we go, because I want a bit of room to do the next bit. Having taken moments, it must now be time to resolve forces, to consider what happens about the sliding. Well, T is my sort of critical value, which I don't want to exceed. What's going to happen with the vertical and the horizontal forces? So, resolving vertically, what have we got? Well, upwards there's R, and also upwards is this component of the tension. So R plus T cos 30, and downwards all we've got is 550, which means I can swap that around to get a statement for R. R is 550 minus T, which by the way is 258 cos 30. So I can calculate all of that and get a value for R, which rounds to 327 newtons to 3 significant figures. But believe me, I'm being careful to keep stored more exact values so that I don't lose accuracy at the very end. Well, that's resolving vertically. Now let's resolve horizontally. Now horizontally I've got friction to the left and T sine 30 to the right. Of course, the friction has to be enough to stop it from moving, but we're told it's going to slide before it topples. So I would say that the value of friction is going to have to be less than or equal to the value of T sine 30. So I reckon friction is less than or equal to 129 newtons to 3 SF. So it just remains to calculate the greatest value of mu. Well, bear in mind that F max equals mu r. That means that mu equals F max divided by r. Well, over to the side here, I've got mu equals the friction divided by the reaction, and I therefore reckon that mu is less than or equal to 129 divided by 327, and that gives me a value which I don't think I can find room to write underneath, of mu is less than or equal to 0.395 to three significant figures. In other words, the greatest value of mu is 0.395 if it's going to slide before it topples. If mu is greater than that, it's going to topple rather than slide. Well, that was quite a long part of the question, for which there are 10 marks, so let's look at where all the marks came from. Firstly, correctly taking moments about P is worth a method mark, and then getting the left-hand side equal to the right-hand side was 3 more answer marks for that complete statement. And there's a 5th mark for finding the value of the tension. And the other 5 marks are allotted as follows: a method mark for resolving vertically, and an answer mark for correctly getting this line here, or the answer 327. A method mark for resolving horizontally. That's 3 marks. The remaining 2 marks come from dividing through as a method to find the value of mu and the numerical value for mu at the end, which is of course the greatest value of mu as required in the question. So there we go. I hope that's helped you refresh your memory about equilibrium of a rigid body. And don't forget to check out the other revision videos for OCR M2 from the FMSP homepage.